Quantization stores and computes model values with fewer bits, but a smaller model file does not automatically generate tokens faster. I'm Mehrdad. In this lesson, we will decide which model values to compress, which layers can tolerate lower precision, and which formats the hardware can accelerate. We will also cover recovery training, key value cache compression, and the product tests required before deployment. Suppose a team converts a model to 4-bit values, so the checkpoint finally fits in accelerator memory. The stored file becomes smaller, and the server may fit more model replicas or larger batches. However, token latency may barely change. The reason is that storage format and computation format are separate decisions. Some serving systems load 4-bit values, convert them back to a higher precision, and then perform the main matrix multiplications at that higher precision. This approach reduces memory use but adds conversion work and does not accelerate the most expensive operations. Faster generation requires kernels that perform those operations directly in the lower precision format on supported hardware. Before deploying a quantized model, ask 2 questions. Does the lower precision reduce enough memory to improve capacity? Does the serving engine execute its main computations in that precision on this accelerator? A 4-bit label answers only the first question unless the engine and hardware documentation confirm the second. If this explanation is useful, like the video and subscribe to follow the series. Quantization can compress 3 different kinds of values, and each choice changes a different serving limit. Model weights are the learned parameters stored in the checkpoint and read during every forward pass. Activations are temporary values created while the model processes the current prompt or generated token. The key value cache stores attention data for earlier tokens and grows with sequence length and active batch size. Lower precision weights reduce the model's stored size and the memory traffic needed to read its parameters. Lower precision activations reduce memory traffic between operations and may enable faster matrix multiplication when the hardware supports that combination. A lower precision key value cache allows the same memory budget to hold more token positions or more concurrent requests. Training precision is another independent choice. A model may train with bfloat 16 and later serve with lower precision weights, activations, or cache entries. When you see a quantization result, first identify which values changed. A smaller checkpoint, faster computation, and larger cache capacity are related benefits, but they are not the same measurement. A transformer contains several groups of parameters, and they do not all respond equally to lower precision. Attention uses query, key, value, and output projection matrices. The feed-forward network usually contains the largest share of parameters through its input, output, and optional gating projections. Quantizing these large feed-forward matrices often saves the most memory, so many serving recipes begin there. Attention projection weights are also common targets, but their sensitivity should be measured for the model and task. Token embeddings convert token identifiers into vectors, while the final output matrix converts hidden vectors into token scores. Some recipes keep these boundary layers at higher precision when exact identifiers, code tokens, or tool arguments become less reliable. Normalization parameters and biases occupy very little memory. Keeping them at higher precision costs little and often avoids unnecessary numerical error. Start by mapping where the parameters are located in the transformer block. Then measure how each group responds before assigning a lower precision. After choosing the target layers, decide how much precision each group can lose without breaking the required behavior. Using fewer bits creates a smaller set of representable numbers. Values must be rounded into that set, and the rounding error can change the model's output. Large feed-forward matrices are attractive compression targets because every saved bit is repeated across many layers. Some activation channels contain unusually large values, often called outliers, which can make one shared scale inaccurate for the smaller values around them. Per-channel or grouped scaling can reduce this problem by using separate numeric ranges for smaller parts of a tensor. A weight-only recipe may store 4-bit weights while keeping activations at a higher precision. This mainly reduces checkpoint size and parameter memory traffic. A weight and activation recipe can accelerate computation when both the hardware and serving kernels support that exact combination. Do not assign 1-bit width to every layer by default. Use lower precision where the parameter count is large and measured task sensitivity is low, while protecting layers that cause important regressions. Bit count alone does not define a quantization format. The format also determines how values are represented, how scaling works, and which hardware operations are available. bfloat 16 is a common higher precision serving baseline. 8-bit floating point reduces memory and can accelerate both wait and activation computation on supported accelerators. 8-bit integers provide another established path, especially on hardware with mature integer kernels. 4-bit integers are commonly used for wait-only compression when memory capacity is the main goal. Newer 4-bit floating point formats target direct hardware acceleration. NVIDIA's NVFP4 uses fine-grained scaling designed for supported Blackwell hardware. MXFP4 is a separate microscaling format with different scaling rules and software support. Similar names and equal bit counts do not make these formats interchangeable. A checkpoint may require conversion, a different kernel, or a different engine before it can run efficiently. Choose the serving format by checking model quality, engine support, kernel support, and the exact accelerator generation together. Otherwise, a theoretically efficient format may only produce a smaller file. Post-training quantization converts an already trained model without running the full training process again. The conversion begins with a calibration set containing prompts that resemble the model's real workload. The calibration pass shows which channels and weights produce large errors when rounded to lower precision. The method then selects scales, groups, or protected values that reduce that error before exporting the quantized checkpoint. AWQ and GPTQ are two established methods in this family. AWQ uses observed activation patterns to protect the weights that matter most for the model's output. GPTQ chooses quantized weights to reduce the reconstruction error of each layer using calibration data. They are alternative approaches, not two required stages that must run in sequence. Both depend on calibration prompts that represent the deployment workload. Generic text may miss sensitivity in code, tool arguments, domain identifiers, or a specialized language. Begin with post-training quantization because it is less expensive than retraining, but evaluate the converted model on the product behaviors that must remain correct. Calibration may not recover enough quality when the target precision is very low, or the model has been heavily fine-tuned. Quantization-aware training addresses this problem by simulating low-precision rounding during training. The model updates its weights while seeing the errors that the final serving format will introduce. After training, the adapted weights are exported into the real quantized format. Quantization-aware distillation adds guidance from a full-precision teacher. The teacher remains fixed, while the quantized student learns to match the teacher's outputs under the low-precision constraint. In this case, the student usually keeps the same architecture and parameter count as the original model. The goal is to recover behavior lost through quantization, not to create a smaller specialist architecture. Start with post-training quantization because it requires less compute and data. If product evaluations still fail, use quantization-aware training when reliable training data is available. Use teacher-guided recovery when the full precision model provides a stronger learning signal than hard labels alone. Both recovery methods cost additional training compute, so compare that cost with using a less aggressive format. After the model weights fit in memory, the key-value cache can become the next capacity limit. Every active token position stores keys and values across attention layers. Using fewer bits for each cache entry allows the same device memory to hold more token positions. That additional capacity can support longer contexts, more concurrent requests, or a combination of both. 8-bit floating point is a common cache format on serving hardware that supports it. Some newer systems also support 4-bit floating point cache formats, which can reduce memory further. Lower precision can change attention scores when the cached keys and values are rounded, so the quality impact depends on the model, context length, and task. Evaluate retrieval over long contexts, exact tool arguments, code, and any behavior that depends on small differences between attention values. Also confirm that the serving engine has an efficient kernel for the chosen cache format. Reduced cache bytes improve capacity only when conversion overhead and quality loss remain acceptable. Quantization can leave an average benchmark score almost unchanged while damaging a behavior that matters to the product. A tool call may use the wrong field, a code model may introduce more syntax errors, or long context retrieval may miss an exact identifier. These failures can disappear inside an average calculated across many unrelated tasks. Build a release evaluation that matches the deployed workload. Include exact match fields, structured outputs, domain terms, long prompts, safety behavior, and the slowest serving conditions you expect. Run the evaluation with the same quantization format, batch size, context length, hardware, and serving engine planned for production. Measure latency and memory alongside task quality because the format must justify its operational cost. Compare important failure rates directly rather than accepting one combined score. If lower precision saves memory but breaks a required behavior, protect the sensitive layer, use a higher precision, or apply recovery training before release. Quantization changes the numeric precision of a model that you have already selected. It usually keeps the same architecture and parameter count. Sometimes the product needs a genuinely smaller model with lower computation, tighter latency, and behavior focused on a narrower task. Distillation trains that smaller model using guidance from a stronger teacher. Video 13b will explain how the transfer works, which training signals are available, and when a smaller student is preferable to a quantized large model. I'm Mehrdad, and I'll see you in the next video.